There are two lines L1 and L2 whose vector equations have been given to us. In the part A, we have to show that the lines L1 and L2 do not intersect. To solve this question, we are going to use a reverse approach, as in, first of all, we are going to assume, let's say the lines are actually intersecting. After you make that assumption, we make some calculations, and if we are able to prove that our assumption was incorrect, that's a way to prove L1 and L2 are not intersecting. So let's start. For the part A, we are going to start with the assumptions that L1 and L2 are actually intersecting. Now, whenever the lines intersect, their x, y, and z coordinates are going to match. For example, R1 is the vector equation of the first line. We can write R1 as x, y, z, and all we'll do is equate the x with the left hand side. So on the left hand side, you will see 3 plus lambda into 2, that is our x. So let's write down the equation. The x coordinate will be 3 plus 2 lambda. Similarly, if we equate the y coordinates on the right hand side and the left hand side, we'll get a 2 plus lambda into minus 2, which when simplified becomes 2 minus 2 lambda. Similarly, z will become minus 1 plus 2 lambda. We repeat the process for the second line L2. R2 is x, y, z. Let's equate the x, y, and z again. X will come out as 2 plus mu, y will be 0 minus mu, and z will be equal to 4 plus mu. So now we have six equations. Let's equate one by one. So let us start with the x equations. Let's equate the equations 1 and 2. So we'll get 3 plus 2 lambda equals to 2 plus mu. And now let's equate the y equations, let's say 3 and 4. So if we equate equations 3 and 4, we'll get 2 minus 2 lambda equals to minus mu. And let's write 5 and 6. So equating the z coordinates, which are equations 5 and 6, we get minus 1 plus 2 lambda equals to 4 plus mu. Now let's try to solve these equations. So let us name these equations as equation A, B, and C. So you can see there are three equations and we only have two variables, lambda and mu. So these are simultaneous linear equations. Let's try to find the value of lambda and mu. Now, if you observe equation A and B, let's add the two equations. So A plus B. On the left-hand side, we'll get a 3 plus 2, and this 2 lambda will get cancelled out because we are adding. So on the left-hand side, we'll get a 5 equals to, on the right-hand side, we have a 2 plus mu minus mu. So mu gets cancelled out, so we get a 2. So we get 5 is equal to 2. Now this equation is absolutely absurd, not possible, right? So since this equation is wrong, which means our original assumption that the lines were intersecting was actually wrong. So let us repeat what is the process which we are using. In questions like this, where we have to prove the lines are not intersecting, we start with the assumption that the lines are actually intersecting. Now, since they're intersecting, we will equate the x coordinates from both equations. We'll equate the y coordinates from both equations. Similarly, the z coordinates, and eventually we'll try to find a value of lambda and mu by solving simultaneous linear equations. But during that solving, if you get something which is absurd, absolutely incorrect, then you can say that our original assumption was incorrect. Hence, finally, we can say that the lines L1 and L2 are not intersecting. And that's how we solve the part A. Let's solve the B part of the question, which is to find the minimum distance between the two lines. So to find the minimum distance between the two lines, let us revise the concept of how to find the shortest distance from a single point to a line. So in this case, we have this red line whose equation is r is equal to a plus lambda b. A stands for the position vector of the point, which is already lying on the line, and b vector is a vector which is parallel to the line. That's how vector equation is defined. Now, P is the point from which we are supposed to find the minimum distance. Since PQ is the minimum distance from the point to the line, we can say that this particular angle is 90 degrees. This angle is 90 degrees. And in the chapter of vectors, remember, whenever we are dealing with 90 degrees, we can use the principle of dot product being equal to 0. But which two vectors do we take? Since PQ is perpendicular to the line, let's write PQ is perpendicular to the given line and the line itself is parallel to the B vector, which means we can say that PQ is perpendicular to B vector. Now, since PQ and B are the two vectors which are perpendicular, that is why we take the dot product between them and put that equal to 0. And how do we find PQ vector? We split it up to form Q minus P. Now, let us go back to the question. We were supposed to find the minimum distance between the two lines. So here, let's draw. We have the line 1, L1, 3, 2, minus 1 will be the coordinates of a point which are lying on the line L1. Then we have the B vector as 2, minus 2, and 2. That's the parallel vector. Similarly, for the second line L2, the point under consideration is 2, 0, 4, and the parallel vector is 1, minus 1, and 1. Now, if you observe only the parallel vectors for both cases, let's say this is P vector and this is Q vector. So observe the pattern between P and Q. If you multiply Q vector with a 2, we will get a P. So P is equal to 2Q. And recall the relation whenever two vectors are scalar multiples of each other, we can say that the vectors are parallel to each other. So we'll say P and Q are parallel to each other. Since the parallel vectors are itself parallel among themselves, which is P is parallel to Q, we can say that the lines are also parallel. Hence, L1 is parallel to L2. L2 is the line which is parallel to L1. So let's say the point is 2, 0, 4, which is given, and the parallel vector in this case will be 1, minus 1, and 1. Now, how do we find the minimum distance? We employ the same principle of 90 degrees. So in this case, let's consider L1. So the point under consideration is 3, 2, minus 1. Since we are supposed to find the minimum distance, we will drop a perpendicular from L1 onto L2. So this angle is 90 degrees. Let's label the points. Let's say this is M and this point is N. So we can see that MN is perpendicular to the line L2 and L2 is parallel to this vector 1, minus 1, and 1. So let's write that down, 1, minus 1, and 1, which means we can write that MN is perpendicular to 1, minus 1, and 1. Since now we have established that the two vectors which are perpendicular to each other are these, now we can take the dot product and put that equal to 0. So Mn dot 1, minus 1, 1 should be equal to 0. And how do we find Mn? You split it apart into N minus M. Now M is that point 3, 2, minus 1. This is the point already lying on L1. That's the point M. So let's write down M as 3, 2, and minus 1. And for the point N, we will use the vector equation of L2. Do not put N as 2, 0, 4. This is a common mistake. So 2, 0, 4 is not N. So N is any random general point lying on L2. So how do we find the coordinates of N? Look at the vector equation for line L2. So let's say R2, let's equate that to X, Y, and Z. So if I equate the X coordinate, X will come out as 2 plus mu into 1. So X will be 2 plus mu. The Y coordinate will be 0 plus mu into minus 1. And finally, the Z coordinate will be 4 plus mu into 1. So which simplifies to 4 plus mu. So these are the coordinates of any random point which is lying on L2. And that's the coordinate for point N. So for N, we will write the coordinates as 2 plus mu minus mu as the Y coordinate and 4 plus mu as the Z coordinate. So this is our N minus M. Let's simplify the overall expression since we are supposed to take the dot product and we have to put that equal to 0. Let's simplify whatever is inside this bracket. So in the X coordinate, you will see 2 plus mu minus 3, which gets simplified to mu minus 1 as the X coordinate. In the Y coordinate, we have minus mu minus 2. So let's write that down. And for the Z coordinate, it is 4 plus mu minus minus 1, which becomes 4 plus mu plus 1, which is 5 plus mu. Now we take the dot product with 1 minus 1, 1 equals to 0. So let's simplify this. How do we take the dot product? We multiply the X components together we multiply the y components together, and we multiply the z coordinates together, and then add everything and put that equal to 0. So let me write everything in brackets so that there is no confusion. And we put all of this equals to 0. So we'll get mu minus 1 plus mu plus 2 plus 5 plus mu equals to 0. So if we simplify this, we will get 3 mu equals to minus 6. This implies mu is equal to negative 2. Now let's go back to the question, what were we supposed to find? In the part B, we were supposed to find the minimum distance between L1 and L2, which is Mn. So how do we find the length Mn? Mn, the length Mn is actually equal to the modulus of Mn vector. So that's what I've written here. Length Mn is equal to the magnitude of Mn vector. And the Mn vector we had found here in this bracket. So this whole bracket is our Mn vector. And how did we find this out? We had done n minus m to arrive at this particular expression. So the value of mu, which we had gotten, was a minus 2. Let's put that in this particular bracket. So we will get mn vector equals to mu is equal to minus 2. So minus 2 minus 1 will become a minus 3 as the x coordinate. And then if you put minus 2 here, the y coordinate will become a 0. And again, if you put mu as minus 2 in the z coordinate, 5 minus 2 will become a 3. So this is our mn vector. Now to find the magnitude of mn vector, we will use the square root formula, x square plus y square plus z square. So we'll get minus 3 squared plus 0 squared plus 3 squared. So this gets us 9 plus 9, which is square root of 18, which simplifies to 3 root 2 units. And this is the final answer. So 3 root 2 units is the length minimum distance between L1 and L2.